So now we'll get into sampling distributions. Alright, we'll consider now all possible samples of size n equals 2. Alright, just again, do something simple. Alright, your possible outcomes are 0 in the first, 0 in the second, 0 first, 1 second, 1 first, 0 second, 1 first, 1 second. Okay, the probabilities of each of these. Alright, since it's like a coin toss, sampling with replacement. Alright, independent probabilities from one to the next. Probability of getting the second outcome is the same as the probability of getting the first, so it's a quarter each. So it's a, sorry, getting really sloppy here. It's a half times a half, and that's a quarter, and it's the same for each of these. Okay, so we have 4 outcomes, all with the same probability of a quarter, and so that adds up to 1. If we're looking at the average outcome, average size of the outcome, instead of just the pure description of the outcome, the average of 0 and 0 is 0, average of 0 and a 1 is a half, average of a 1 and 0 is also a half, and 1 and 1 average of 1. And so we still have, of course, a quarter probability for each of these. If we wanted to write a nicer looking probability distribution for this, we would have the distribution of x bars and the probability of each of those. Alright, so our outcomes for in terms of averages are 0, a half, and 1. Okay, 0, half, and 1 are our possible outcomes. Probabilities of those, well, the 0 has a probability, is one way of getting a 0. The probability of that one way is a quarter. A half, there are 2 ways. Probability of one way is a quarter, so 2 times a quarter, or a quarter plus a quarter, is a half. And the 1, there's one way of doing that. Probability of that one way is a quarter. Okay, so this is our probability distribution for all possible samples of size 2 from our population above. Okay. Alright, let's find the mean and standard deviation variance of this sampling distribution. So we'll replace previously where we had x bars, x's, we'll replace those with x bars. So instead of x p of x, we'll have x bar p of x bar, and then we'll have x bar squared p of x bar. Okay, then the notation, we've done things like this before. So 0 times a quarter, 0, a half times a half is a quarter, 1 times a quarter is a quarter, and that adds up to a half. Alright, so this is sigma x bar p of x bar, and this will be the expected value of the x bars, or if you like, the mean of the x bars. But since that's always equal to the population mean mu, we quite often just drop the x bar subscript and just say that the mu is a half. Right? So this half is the same as the half that we had for the mean of the population. Variance is not the same. Okay, so x bar 0 squared times a quarter is 0. half squared is a quarter times half is 1/8, and 1 squared is 1 times a quarter, 0.25. Okay, and that adds up to 3/8, 375. So this is sigma x bar squared p of x bar. So the variance of the x bars is equal to the formula first, sigma x bar squared p of x bar minus the mean of the x bars, if you like, squared. Again, this formula might look strange and cumbersome to some, but guess what? If you just replace the x's when we did the mean variance of a probability distribution with x bars, we have the same formula. Alright, so sigma x bar squared p of x bar is the addition of the last column. It's 375 minus the mean of the x bars, or the mean 0.5 squared. Alright, it's 375 minus 0.25. I'm doing that right. That's a quarter, 0.125. So when we have sample size n equals 2, right, the mean, variance, and standard deviation of all possible sample means go as follows. So mu sub x bar is equal to the population mean of a half. The variance, sigma squared sub x bar was equal to, right, 0.125, which is less than the variance of the population. Variance of the population was 0.25. It's always less. It always actually turns out that sigma squared sub x bar is equal to sigma squared divided by n. So in this case it would be 0.25 divided by, divided by sample size 2. Okay, and that boils down to, a quarter times a half, and that's 1/8, 0.125. Okay, but in general, we're not concerned about variances because we're going to deal with normal distributions. So what we'll worry about is the standard deviation of the distribution of x bars, and that formula will be sigma divided by the square root of n. Right, essentially exactly the square root of this formula. So this is the standard deviation of the sampling distribution. Now I've slid a little bit fast over this, but the marvelous thing about all this stuff is that these facts, that mu x bar is equal to mu and sigma sub x bar is sigma divided by square root of n, is true for any population that you can find. Okay. Population doesn't have to be nice. It can be ugly looking. It could be very strange. This will always happen. Okay. So we could now go to samples of size 3, 4, and show you the same stuff. Okay. But if you think about it, at least for the average of the sample averages is always got to equal the population average. Given our little example here, it'll happen for larger sample sizes. For more difficult populations where instead of 2 items you've got any number of different items. It'll always happen. By the way, you might think, well, this is great, but doesn't always happen. For instance, if we try to do a sampling distribution of the sample medians, the thing becomes messy and difficult and intractable in a hurry. There are no nice sampling properties for the median, and therefore the median, even though it's nice and useful for small samples, since it has horrible sample properties, we never use it when it comes to sampling theory. Well, sorry, not never, but very rarely use it in terms